Assalamualaikum students. Students, today we are doing ideal gas, right? Now, what is an ideal gas? Actually, ideal gas is the gas which has no intermolecular forces. Students, when we discuss solids, liquids, and gases, when we describe that these are three states of matter and with the particles are very close and far apart, like when we describe all these different states of matter, the liquids, the solid, the gases, the movement of the particle, the forces of attraction, we actually describe all these three states according to kinetic molecular theory. According to kinetic molecular theory, ideal gas is the one in which there is no intermolecular forces or negligible intermolecular forces. The particles have mass, but they have no volume. They don't occupy any space. The volume of the molecule is negligible as compared to the volume occupied by the gas. I'm going to explain all these, but first giving a quick read to the points that there is no intermolecular forces. The molecule have mass but no volume, or the volume of the molecule is negligible as compared to the volume occupied. Collision between the molecules is perfectly elastic. Particle move in a straight line, collide, straight line, collide, straight line, collide. When molecules collide with the wall of the container, they exert pressure. The average kinetic energy of the molecule is proportional to the absolute temperature. Now, coming to this, look, coming to this, look. This is a gas. These are 1, 2, 3, 4 molecule of the gas. The occupied volume is how much? 100. This is the occupied volume, which is suppose 100 centimeter cube. Each molecule, for example, each molecule is 0.1. So do you think the 0.1 is negligible as compared to 100? I don't think so. 0.1 is not negligible as compared to 100. But if I expand the gas, how can you expand the gas? You will increase the temperature. You will lower the pressure. Like, look, this is container. At high pressure, they're closed. But if I lower the pressure, the particle expand. So, if I increase the temperature and decrease the pressure, the gas will expand. Is there any change in the volume? No. But is there change in the occupied volume? Yes. Now the occupied volume is how much? 100,000, for example. So do you think that 0.1 is negligible as compared to this? Yes. And if I expand it further, and now the occupied volume is, for example, some 100,000 centimeter cube. So can we say that 0.1 is clearly negligible as compared to this? Yes. So what are my conclusions? In this state, the particles are so far that they don't interact each other, no intermolecular forces. The volume of the molecule is negligible as compared to the container, of course. So what is an ideal gas? Ideal gas is the one in which the particles are far apart, they don't have any intermolecular forces, the actual volume is negligible as compared to occupied volume. When the particle move, they move in a straight line, but once they collide, They will change their path but still moving in straight line. So, if I look at A, B, and C, which one is the most ideal? C. So, among B and C, which one is more ideal? C. Among B and A, which one? B. So, do you think ideality is absolute? No, it is relative. Relative to A, B is more ideal. But relative to C, B is less ideal. So, ideal gas is what? When the particles are far apart. Ideal gas has no intermolecular forces. The particles move independent of each other. They are far apart. The occupied volume is so large. The occupied volume is so large that its own volume is negligible. The particles far apart, no interaction, no attraction, no repulsion. The real gases, they become ideal. The real gases like carbon dioxide, HCl, ammonia, they become ideal when you increase the temperature and when you lower the pressure. When you expand the gas, the particles get far apart. No gas is 100% ideal. Now, when the temperature increases, when the pressure increases, the molecules get far apart and the gas is getting more ideal. How to find out the most ideal gas? How to find most ideal? Most ideal is the one which is at high temperature and low pressure. First check the condition. Like to find out that which gas is most ideal, like which one is most ideal. You know what you're supposed to do first? First criteria is what? Condition. You have to select the one which is at high temperature and low pressure. High temperature, 500, 500, low temperature, cancel it. Reject low temperature. You know, all the gases listed are at the same pressure. So the pressures are same for this question. If the pressure is same, the criteria is now what temperature? Which temperature? High temperature. The low temperature is what? Cancelled. After, after temperature and pressure are the condition. Next thing is, if the conditions are same, then the gas with the weakest ID, that is the one with the less number of electron, is the most ideal. So 100 Kelvin and 100 Kelvin, low temperature, cancel. Ammonia at 500 and neon at 500. The 500 is same. Now, ammonia has strong hydrogen bonds, which are very strong intermolecular forces. But neon has just ID. So which one is most ideal? Neon. Now, now, look. First, what is an ideal gas? The gas with no intermolecular forces, the gas in which the particles are far apart, they don't interact, there is no intermolecular forces, their actual volume is negligible as compared to occupied volume. Next point, how to find out that which gas is the most ideal? Gas most ideal. So what you are supposed to do? First check temperature must be high, pressure must be low so that the gas expand. But if the conditions are same, what is your next criteria? The type of intermolecular forces. So which gas? ID with lowest electron. Most ideal. Now if I ask you this question, which of the following would behave most like an ideal gas? Among these, which one is most ideal? Look, carbon dioxide. Carbon dioxide is symmetrical molecule. The corner atoms are same. The dipoles cancel out. This is what? A non-polar molecule, no permanent dipoles. So it has what? ID. Helium IDID, hydrogen IDID, nitrogen IDID. They're all having IDID. So IDID depends on what? IDID getting weak as the number of electron decrease. This is what? 6 plus 8 plus 8, 22 electron, 2 electron, 2 electron, and nitrogen, 7 plus 7, 14 electron. So which one have most electron? Carbon dioxide. IDID strongest. Look, this is 22 electron, this is 14 electron, this is 2 and 2, but hydrogen has more surface area. Hydrogen are 2 and helium is just 1. The hydrogen has more surface area of contact and helium has less surface area of contact. So this one is the most ideal. Another question. Least like an ideal gas. Ammonia. This is ammonia. Ammonia is what? Hydrogen bonding. Fluorine is what? IDID. Krypton is also what? IDID. Fluorine, both are same. No permanent dipoles. Krypton, no permanent dipoles. Hydrogen bond, hydrogen bond. So, these two has IDID. This one has 36 electron and this one is having just 18 electrons. So, among these, this one is more ideal because less electron, more electron. But if I compare water and ammonia, what you will see? What you will look for? In ammonia, there is hydrogen bond. In water, there is hydrogen bond. But in water, there are two lone and two hydrogens. There's one lone and three hydrogen. So the lones are less. So it has one hydrogen bond per molecule. It has two hydrogen bond per molecule. So this is what? Two hydrogen means more hydrogen bonds, least ideal. And this one is what? Most ideal. Your next topic, volume of gas. Look, if I explain this separately here, volume volume of gas. Number one, volume is directly proportional to moles. Volume is directly proportional to moles. Second, volume is directly proportional to temperature for a fixed mass and pressure, right? The temperature must be in Kelvin. Volume is directly proportional to what? Temperature. 0 Kelvin. You know what is 0 Kelvin? 0 Kelvin is minus 273 degrees Celsius. The temperature at which the movement stops, ceases. The volume of the gas is 0. No gas at minus 273 degrees Celsius, 0 Kelvin. Now, if the pressure and temperature are constant, not changing, the volume is directly proportional to moles. If moles and pressure are same, constant throughout, volume is directly proportional to temperature. Third, volume is inversely proportional to pressure. Now see, if volume is inversely proportional to pressure, I'm going to explain this. Look, volume is inversely proportional to pressure. Hmm? Suppose the pressure is 1, the volume is 4. Hmm? When you increase the pressure, the volume will decrease. Increase the pressure, volume decrease. Increase the pressure, volume decrease. When the pressure is more, volume is less. Look, volume is inversely proportional to pressure. If I remove the sign, this is what? Constant. If I bring the pressure on the other side, PV is what? Means when the pressure increase, the volume decrease in such a way that the product remains constant. Like look, this is P, this is V, this is what PV. So when the pressure was 1, the volume was 4. Volume is 4. It's 4. When you increase the pressure, volume decrease in such a way that it is still 4. When you increase the pressure, it becomes what? 1.33, still 4. So look, when you increase the pressure, the volume decreases in such a way that their product remains constant. 1 and 4, 2 and 2, 3, multiply this, it becomes what? 4, 4 and 1. Huh? Pressure increase, volume decrease, but the PV remains constant for an ideal gas. So, for any ideal gas, for example, look, this is V and P. This is 0, 1, 2, 3, 4, 5. This is 0, 1, 2, 3, 4. When the pressure is 1, when the pressure is 1, the volume is 4. When the pressure is 2, the volume is 2. When the pressure is 3, the volume is 1.3. When the pressure is 4, the volume is this. So, how is your curve? Is it like this? No, it's always a curve like this. When the pressure is more, when there is low pressure, volume is more. When there is high pressure, volume is less. But it will be like this. Okay? Now, another graph. For instance, this is what? PV against what? P or V. Whatever is the pressure, suppose it's 0, or simply we start with 1, okay. 1, it's what? 4. 2, it's still 4. 3, it's still 4. So the graph would be like this. Coming to this, look. Volume is directly proportional to moles. Volume is directly proportional to temperature. Volume is inversely proportional to pressure. So, when the pressure increase, the volume decrease. I'm repeating the same thing. So, if you plot volume and pressure, the curve would be this way. It's never like this for any inverse relation. Right? And the graph of the PV is what? Straight line. The PV is not changing. At 1 it is 4, at 2 it is 4, at 3 it is 4, so it remains the same. But if I do the same experiment at helium, at ammonia, like if I do this for real gases, what will happen? Come. Look. I did the same experiment with, suppose, ammonia. When I increase the pressure, When I increase the pressure, the particle gets closer, the ammonia gets closer. When the ammonia gets closer, there will be hydrogen bond. When there will be hydrogen bond, would it be any longer ideal? No, because the molecules will start attracting each other. Like when you use real gases, not look, the pressure increase, the volume decrease, the PV remains constant for an ideal, which is not even a real gas, which is a hypothetical situation. For a hypothetical gas, it would be constant. But if I do the same for real gases like ammonia, when the pressure is more, the particle get closer. When the particle get closer, you increase the pressure, the particle get closer. When ammonia gets closer, there will be what? Hydrogen bonding. When there will be hydrogen bonding, they attract each other. When they attract each other, it's no longer ideal. You know how your graph would be. It would be like this. Look. This is PV against P. For an ideal, it's like this. But if I do the same experiment for ammonia, this is low pressure. This is high pressure. At low pressure, the graph starts exactly at this point. This shows that ammonia is ideal at low pressure. But the moment I increase the pressure, the graph is like this. Initially, they get very close because of hydrogen bonding, and when they're further brought closer by high pressure, they start repelling each other. Not ideal. At this point, it's ideal. But ammonia has very strong hydrogen bond. The moment you increase the pressure, it becomes less ideal. If I do the same experiment for carbon dioxide, if I do the same experiment for nitrogen, if I do the same experiment for helium, so which one is most ideal? Helium. Why? Because it has weakest ID, 2 electron, ID, 14 electron, ID, 22 electron, and hydrogen bond. So, at low pressure, they're ideal, but the moment you increase the pressure, ammonia showed deviation due to strong hydrogen bond, and helium is closer to ideal due to ID. So, we know that volume is directly proportional to moles. Volume is directly proportional to temperature, inversely proportional to pressure. If I combine, volume is directly proportional to temperature in moles, but inversely proportional to pressure. If I remove this sign, I will put what? The constant, the ideal gas constant. NT over pressure. If I bring the pressure to the other side, PV is equal to what? RNT. And can we write it just this way? nRT, yes, of course. This is ideal gas equation, right? This is ideal gas equation. This is 8.31 on the last page of the paper. It's always given. These are what? Moles. These are what? Moles. This is temperature must be in Kelvin. Must be in Kelvin. Suppose there is this X degree Celsius, so plus 273, it will turn into Kelvin. Right? Now, the next very, very, very important thing, keep in mind, if you have pressure and volume, you must know if the pressure is Pascal, volume must be in meter cube. If it is kilopascal, It must be in dm cube. Now, 1 atmosphere is equal to 10 power 5 Pascal divided by 1000, 10 power 2 kilopascal. You must know this conversion factor, right? Temperature, you must know. Degree Celsius plus 273 becomes Kelvin. Hmm? Third, third. The third is if you have suppose x x centimeter cube, right? So divided by 1000, it becomes what? Dm cube. X centimeter cube divided by 1000 into 1000. It's what? Meter cube. Hmm? So this is cm into dm. Now, x dm cube divided by just 1000. You get what? Meter cube. So in the question, you have to look at the Pascal, kilopascal, and meter cube conversion. If they give you something in pressure and kilopascal, why you will shift both the units? If it is kilopascal, put this in D. Perfect answer. Right? So, how can you convert cm divided by 1000 dm? Cm divided by 200,000 meter cube, and dm into meter is divided by 1000. Come to this topic here. Look. When the pressure increase on the real gas, the molecules get closer, they experience intermolecular forces, and the volume of the molecule and the volume occupied gets small. As a result, the actual volume of molecule is no longer negligible as compared to the occupied volume. As a result, the gases deviate from the ideal behavior. The gas with stronger intermolecular forces deviate most. And then what we did? The relation of the volume with the moles, with the temperature, with the pressure, combining, you get this constant here. The constant is called what? Ideal gas constant. It is given on the last page of the paper, right? Its value is what? 8.31. You must know that, the pressure, if Pascal, it must be meter cube. If it's kilopascal, it must be dm cube. So, cm into dm divided by 1000, cm into meter divided by 2000, like 1000 into 1000, and dm into meter divided by just 1000. I've told you all these conversions. Sorry, all these conversion. And now look, last thing. If your PV is equal to nRT, what is N? It is mass over MR into T. Now, if I bring this volume down on the other side, how I'm supposed to write? What is M by V? Density. This is what? Density, MR, RT. You know, all these are ideal gas equation. The only thing about which you must be very careful, for Pascal, it's meter cube. For kilopascal, it is It is dmq. This is always Kelvin, right? So we can calculate the pressure, the volume, the mass, the MR, the temperature. R is always given. Like if all the other factors are known and only one is unknown, we can find it so easy. But we must be careful about the units. And when they ask you to identify gas, what you are supposed to do, find its MR. For example, look at this question. For all these notes, you have to go to my website, right? You can find all these on my website, Chemistry by Zeenat. Look at this question. Hmm? In this question, you should assume that the vapors behave like an ideal gas. This much gram of the volatile liquid from vapors, gas, at this much meter cube, volume of this much, 0.175 gram of volatile liquid produces vapor of this much volume at this much temperature, at this much pressure. And what you're supposed to find? MR. Okay, perfect. You have this much liquid and you converted the liquid into gas. When you convert a liquid into gas, its density will change, its volume will change, but mass remains same. So we know the mass, we can find MR. We know the mass, we can find MR. But we need to put the pressure and the volume and the temperature. The temperature is in Celsius, so plus 273 Kelvin. It's Pascal and it's meters. They're perfect. For Pascal, you will use meter. So put the values, you will get the MR. The MR is what? 90. Another question. What is the volume of the steam produced when 1 gram ice? So if 1 gram ice turn into vapors, the vapors would also be 1 gram vapors. So we know the mass. Huh? It is what? 1 gram H2O gas. We know the mass. MR is what? 18. So 1 over 18. And you need to find what volume. But when you need to find the volume, it's kilopascal. So with kilopascal, it would be dm. So I'm going to put the kilopascal. I will get my answer in dm cube. And this is plus 273, 596. And you get the volume. Finish. So these are questions. The topical questions, you can find all these topicals on my website, Chemistry by Zeenat, and all the notes. You can see the notes. Everything is given, the concept of the ideal gas in the beginning, then how to find the most ideal gas, and then the next volume of the gas and volume of the gas, and then the PV is equal to nRT derivation, kind of derivation, right? And then the conversion factors, and then how to relate, how to bring the density and all these things combined, like they're all the same ideal gas equation, right? They're just the moles are replaced by mass over mr, and then m by v is turning into density. All are ideal gas equation. When question is asked about the gas identity, find the mr. Be careful about units, the units conversion, everything given. I hope you understand. Do the practice, and if I get time, I will solve some question for you people. But I hope if you follow all these guidelines, you will be able to do almost 70-80% question. Maybe you have some problem. There are a few questions which are difficult, right? And I will do these uh, in the end of the March, when I will be doing the yearly papers with you people. I will talk about these questions. Okay. Don't forget to like and subscribe and share my channel. Allah Hafiz.